Hello everyone, welcome back to my YouTube channel Learning with Deepu. I'm your Deepu from SVC. In today's video, I will be discussing on static hashing. What is hashing? Hashing is a data structure technique that allows efficient data retrieval using a hash function. A hash function converts input like a key into a fixed size string of bytes. This hash code determines the index in a hash table, where the data tables will be stored or retrieved. Hashing is widely used in databases, cache systems, and dictionaries to speed up data access. Static hashing. Static hashing uses a fixed size hash table determined when the table is created. In static hashing, the number of slots, buckets in the table is constant, even if the amount of data changes. Each record is assigned to a slot based on its hash code, and the position in the table never changes. Performance is steady, but the table can become inefficient if too many collisions occur or the table is underutilized. Hash function. The hash function in static hashing is a key to disrupting records evenly across the hash table. Reminder method. Division reminder method. The key is divided by the table size and the reminder is used as the index. Multiplication method involves multiplying the key by a constant and using fractional part as the index. A well-defined hash function minimizes collisions, maximizing efficiency. A static hash table. Collision resolution. Collisions occurs when two different key hash to the same table index. In static hashing, the most common methods for handling collisions are chaining. Uses a linked list at each index to store all elements that map the same slot. Open addressing searches for the next available slot within the table when a collision occurs. Linear probing searches sequentially for the next available slot, whereas quadratic probing uses quadratic intervals to find an empty slot. And double hashing uses second hash function to determine the interval between props. Advantages and disadvantages of hashing. Advantages of static hashing: simplicity, easy to implement and straightforward to use. Whereas disadvantages of static hashing: limited scalability. The fixed size of the table can lead to inefficient memory usage if data volume changes significantly. Predictable performance. Since the table size is fixed, performance remains consistent. Whereas in disadvantages, high collision rate. As the table fills up, collision becomes more frequent, reducing performances. Memory efficiency. No dynamic memory is allocated overhead once the table is created. Wasted space. If the data set is smaller than the allocated table size, memory is underutilized. Static hashing versus dynamic hashing. Static hashing. Fixed table size. Performance predictable, inefficient with large datasets or changes in size. Whereas dynamic hashing allows for growth and shrinkage of hash table size based on the volume of data. Dynamic hashing adjusts its structure to reduce collision when the table becomes too full. In real world application, dynamic hashing is often preferred in databases and systems that require scalability. Real world applications of hashing. Databases hashing is widely used for indexing to ensure fast retrieval of records. Caching. Web servers uses hash-based caches to store frequently accessed data pages, whereas cryptographic hash functions are used for data integrity and security, such as in digital signatures. Compiler design. Symbol tables in compilers use hashing to quickly look up identifiers. Performance considerations. Load factor. The load factor is the ratio of the number of stored elements to the size of the table. A high load factor increases the chance of collisions, reducing efficiency. Hash function quality. A good hash function minimizes collisions and ensures an even distribution. Collision resolution strategy. The efficiency of handling collisions directly affects overall performance. Future directions in hashing. Dynamic and elastic hashing. Future systems focuses on dynamic and elastic hashing to handle big data efficiently. Consistent hashing used in distributed systems like cloud computing to evenly distribute data across servers. Improved collisions handling. Research is ongoing into more efficient ways to resolve collisions in hash tables. Hashing in machines learning. Hashing in machine learning. Emerging applications of hashing in data deduplication and feature hashing in machine learning. Hashing algorithms. Hashing algorithms create hash code that map the data to the table indices for efficient retrieval. Popular algorithm includes MD5, SHA1, SHA256 and CRC32. These algorithms vary in terms of complexity, collusion and resistance and speed. For static hashing, simpler hash functions are often used for faster performances. Hash table implementations. Hash table are implemented as arrays uh, where indices correspond to hash codes. Hash table can be implemented using chaining or open addressing for collision resolution. In changing, each index points to a linked list of entries that share the same hash. In open addressing, elements are stored within the table. Alternative are used if collisions occurs. Types of hash functions. Division-based hashing uses the modulus operation to compute index. Multiplication-based hashing involves multiplying by a constant and using the fractional part. Universal hashing uses a random function to reduce collision probability. Choosing the right hash function can impact performance as collision handling. Collision resolution techniques analysis. Chaining efficient but may require additional memory for linked list. Open addresses. Reduced memory usage might lead to cluster linear probing, simple but susceptible to primary clustering. Quadratic probing reduces clustering but requires an ideal table size. Double hashing effective at dispersing entities but more complex to compute. Load balancing in hash tables. Load factor defines the fullness of a hash table. A high load factor can lead to more collisions. Rehashing may be used when the load factor exceeds a certain threshold. Good load balancing ensures consistent performance by minimizing collision rates. Real-world performance challenges. Memory constraints. Hash table require significant memory, especially for large data sets. Scaling. As data grows, static hash tables can struggle with high collision rates and low efficiency. Latency. In high performance applications, mm, even small delays from collisions can impact user experience. Overcoming these challenges require careful planning and potentially the use of dynamic hashing. Conclusion. Static hashing is a valuable technique when the size of the data set is known and fixed. It provides predictable performance and efficient for small consistent datasets. However, its limitations in handling dynamic data growth and collisions make it less suitable for scenarios with varying data sizes. Overall, static hashing is a foundational data indexing but often gives way to dynamic hashing in modern applications. By this thing, I'm going to end the video. Thank you for watching till here. Please do like, share and subscribe. See you in the next video. Thank you.